morning to everyone. This is Jakudipti of Branch Aeronautical Engineering bearing roll number 23951A2114 of semester 6. Today I am here to give presentation on behalf of AAT2. The subject is Computational Aerodynamics and Turbulence Modeling. For this I have chosen the topic Modeling Laminar to Turbulent Transition on a Micro UAV Wing Surface. So let us enter into the introduction. Micro unmanned aerial vehicles, which are known as micro UAVs, operate at low Reynolds numbers due to their small size and low flight speeds. Typically, the Reynolds number for such systems ranges between 10 to the power of 4 and 10 to the power of 6. In these regimes, the aerodynamic behavior of the flow over the wing surface is significantly different from that of conventional aircraft. One of the most critical aspects of this behavior is the transition from laminar to turbulent flow within the boundary layer. This transition strongly influences lift, drag, and overall aerodynamic efficiency. One of the most critical aspects of micro UAV aerodynamics is the transition from laminar to turbulence over the wing surface. Initially, the flow near the leading edge of a wing is laminar, characterized by smooth and orderly motion. However, as the flow progresses downstream, disturbances grow, leading to a transition into turbulent flow. This transition is not instantaneous but occurs over a region influenced by factors such as surface roughness, pressure gradients, and external disturbances. Understanding and accurately predicting this transition is essential because it directly affects the lift, drag, and stall characteristics. In low Reynolds number flow, a phenomenon known as a laminar separation bubble often occurs. This happens when the laminar boundary layer separates from the surface and then reattaches after transitioning to turbulence. Such behavior can significantly degrade aerodynamic performance if not properly accounted for. Traditional CFD approaches often assumes fully laminar or fully turbulent flow, which can predictions of micro UAV applications. Therefore, advanced transition models are required to capture the physics of transition process accurately. Among these, the transition SST gamma RE theta model has emerged as a reliable and widely used approach. This project aims to model the laminar to turbulent transition on a micro UAV wing using CFD tools. By doing so, it seeks to predict a deeper understanding of boundary layer behavior and its impact on aerodynamic performance. The study also emphasizes the importance of proper mesh generation, boundary condition selection, and turbulence modeling. Micro unmanned aerial vehicle micro UAVs has gained significant importance in recent years due to their wide range of applications including surveillance, environmental monitoring, defense operations, and indoor navigation. Unlike conventional aircraft, micro UAVs operate at low flight speeds and small characteristic dimensions, resulting in low Reynolds number flows, typically in the range of 10 to the power of 4 to 10 to the power of 6. This low Reynolds numbers regimes introduces unique aerodynamic challenges, particularly in terms of boundary layer behavior. One of the most critical phenomena in micro UAV aerodynamics is the transition from laminar to turbulent flow over the wing surface near the leading edge of the wing. The flow is generally laminar, characterized by smooth and orderly motion of fluid particles. As the flow moves downstream, disturbances grow due to instabilities, eventually leading to transition into turbulent flow, which is generally high chaotic and mixed. The boundary layer concept. When air flows over a wing surface, a thin region known as the boundary layer develops due to the no-slip condition of the wall. Within these layers, the velocity of the fluid changes from zero at the surface to the free stream velocity away from the surface. The boundary layer can exist into two primary states. One is laminar and turbulent, another is turbulent. The nature of these layers plays a crucial role in determining aerodynamic performance. So, first of all, coming to laminar flow characteristics. Laminar flow is characterized by smooth, orderly motion of fluid particles in parallel layers. In this regime, there is a minimal mixing between adjacent layers, resulting in low skin friction drag. Laminar flow is typically present near the leading edge of the wing, especially under low Reynolds number condition. However, laminar flow is inherently unstable and susceptible to disturbances. Turbulent flow characteristics. So, turbulent flow is highly chaotic and involves significant mixing of fluid particles. It is characterized by fluctuations in velocity and pressure. Although turbulent flow has higher skin friction drag compared to laminar flow, it has higher energy near the wall, which helps in delaying flow separation. This makes turbulent flow beneficial in maintaining attached flow over the wing surface. So the transition mechanism includes the transition from laminar to turbulent flow does not occur abruptly but rather over a region where instabilities grow and amplify. This process is influenced by various factors such as surface roughness, pressure gradients, and external disturbances. One of the primary mechanisms of transition is the amplification of small disturbances known as the waves. These waves grow in amplitude as they move downstream, eventually leading to breakdown into turbulence. So the objective of this project is, the primary objective of this study is to model and analyze the laminar to turbulent transition on a micro UAV wing surface using computational fluid dynamics. This involves understanding the physical mechanism responsible for transition and accurately capturing them through numerical solutions. One of the key objectives is to study the behavior of the boundary layer over a micro UAV wing operation at low Reynolds numbers. The boundary layer plays a crucial role in determining aerodynamic forces, and its transition from low laminar to turbulent flow significantly attaches lift and drag characteristics. By analyzing this transition, the study aims to identify the factors that influence aerodynamic performance. The methodology which we have used are, the methodology adopted in this study involves a systematic approach to modeling the laminar to turbulent transition using computational fluid dynamics, which is CFD. The simulation is performed using ANSYS Fluent, which provides advanced models for transition prediction. The first step involves selecting an appropriate airfoil geometry representative of a micro UAV wing. Commonly used airfoils such as NACA series are suitable due to their well-documented aerodynamic characteristics. Geometry is created or imported into CFD environment. The overview of approach is, the methodology approach adopted in this study focuses on modeling the laminar to turbulent transition over a micro UAV wing surface using CFD. The simulation is carried out using ANSYS Fluent, which provides advanced turbulence and transition model suitable for low Reynolds number flows. A systematic approach is followed, including geometry creation, mesh generation, solver setup, and post-processing. Then we'll select the geometry selection, then mesh generation will take place in the ANSYS. Then we'll be applying the boundary conditions, which are appropriate boundary conditions are applied to simulate realistic flow conditions. A velocity inset defined with a specified free stream velocity and low turbulent intensity, typically between 1% to 5%. A pressure outlet boundary condition is applied at the downstream boundary. The airfoil surface is treated as a no-slip wall, ensuring the fluid velocity at the surface is zero. These conditions help in accurately representing external aerodynamic flow. Then coming to solver and model selection, which is done in the Fluent. Next, solution initialization and conversion. Then post-processing and analysis. After convergence, the results are analyzed using post-processing tools. Velocity contours, pressure distribution, turbulence intensity, and skin friction coefficients are examined to identify the transition region. The formation of laminar separation bubbles and flow reattachments are also studied. This analysis provides insights into the aerodynamic behavior of the micro UAV. Then coming to the results and discussion. The results obtained from CFD simulation provides valuable insights into the laminar to turbulent transition on the micro UAV wing surface. The analysis focused on key aerodynamic parameters such as velocity distribution as discussed, pressure coefficient, turbulent intensity, and skin friction. The velocity contours indicate that the flow remains laminar near the leading edge with smooth and uniform streamlines. As the flow progresses downstream, distribution begins to grow, leading to the onset of transition. This is observed as an increase in turbulence intensity and fluctuations in velocity. One of the most significant observations is the formation of the laminar separation bubble. Conclusion. At last, I would like to terminate this project by saying that this study successfully demonstrated the importance of modeling laminar to turbulent transition on micro UAV wing surfaces. The transition process plays a crucial role in determining aerodynamic performance, particularly in low Reynolds number. The use of transition SSC gamma RE theta model in ANSYS Fluent provided effective in capturing the transition phenomena and predicting the behavior of the boundary layer. The model was able to accurately simulate the onset of transition, the development of turbulence, and the formation of laminar suppression bubble. The results shows the laminar suppression bubble significantly influence lift and drag characteristics. These bubbles can reduce aerodynamic efficiency and lead to early stall if not properly merged. Therefore, understanding and conditioning transition is essential for improving micro-UAV performance. The study also highlights the importance of mesh quality and boundary condition selections. A fine mesh with proper inflation layers or appropriate turbulent intensity values is necessary for accurate simulation results. In conclusion, transition model is a critical aspect for micro UAV aerodynamic analysis. It provides valuable insights into flow behavior and helps in optimizing wing design for better performance. Future work can focus on experimental validation, unsteady simulations, and the use of advanced model for improved accuracy. Thank you for giving this opportunity.